think I might be overstating certain things, but okay. The bottom line is, if your function f of x looks like this or this, then the function values are increasing or decreasing at a constant percent growth or decay rate. The function values are changing by a constant percent. You know, they're increasing or decreasing by a certain percent. Yeah, question?
So this equation for you used it for graphing?
Well, we're not going to graph it though.
Oh, okay.
This is when the function values are going to be increasing or changing by a constant percent. You know, like the function values might be increasing by 5%.
Okay.
Not really. Okay, well, let's do an example. Maybe that'll help us. I mean, this is just another example. Let's suppose our function looks something like this. Okay. So in this case, what's going to happen is our A is 100, which is our initial value. R is 0.35, which is in this case our decay rate. So this means the function values will be decreasing by 35%. If we increase x by 1 unit, the function values will decrease by 35%. And so these are the function values. When x is 0, we have f of 0 is 100. When x is 1, again, if you just plug it in directly, you're going to get 65. Okay, so you have a quantity here that's decreasing from 100 to 65, right? If you calculate the relative change, so when x is 0, you have the starting value. When x is 1, you have the ending value, right? Here. We get negative 0.35, which really means the function value is decreasing by 35%. Over here, okay, when x goes from 1 to 2, right? So the function value is changing from 1 to 2. Here, it's going from 65 and it's decreasing to 42.25. Okay, so what is that change? Well, the relative change there, right? So the starting value is f of 1. The ending value is f of 2, right? If you calculate the relative change, you get this again, which means the function values here, from f of 1 to f of 2, the function value is decreasing by 35%. And that's always going to happen. If you start x at any number and you increase x by 1, you know, from 0 to 1, 1 to 2, the corresponding function values are going to decrease by 35%. So if you were to calculate the relative change, you would get negative 0.35. And then, of course, you convert that to a percent, and you would get negative 35%. And again, that means the function values are decreasing by 35% here. Okay, and that's really what this is saying. Okay, so that's one example. Okay. All right, so the next slide, I know this stuff's confusing. The next slide here is kind of summarizing what I'm trying to say. Okay, basically that for a constant percent change, if you have f of x here, again, this kind of function, this is an exponential function. With this function, this is going to happen. This is the relative change. And this is saying, again, when you increase x by 1 unit, or just 1, the function value, the corresponding function values will increase by r times 100%. I mean, here r is a decimal, so you have to convert it to a percent. So in this case, the function is increasing by at a constant percent rate, whereas here the function values are decreasing at a constant percent rate. Okay? Like so. All right, good. I mean, this is just summarizing what I'm trying to say. So again, it's not like with linear functions where the function values increase or decrease by a constant number, the slope. Here they're increasing or decreasing by a constant percentage. And this kind of function has a lot of nice, it gives us a lot of nice implications, or as you can see here, let's say you want to make an exponential function to have a growth rate of 16%, whose initial value is 100. So in other words, you want an exponential function, okay, to have a growth rate to increase by 16%, whose initial value is 100. So here you would have your R, you would use f of x equals to a times 1 plus r, because there you'll have increasing percent change. It'll be increasing. You take your r to be 0.16, and your function will look like this. Because again, you want it to have a growth rate of 16%. The initial value is 100, so it's going to be 100 times 1 plus r, and r is 0.16. But yeah.
So are you basically just like plugging in the percentage and just like converting it to a decimal?
Basically, yeah.
And then just switching the sign for whether or not it's growth or decay?
Exactly.
Oh, okay.
That's all it boils down. I mean, I might be over-explaining it, but essentially that's what it boils down to.
Okay. Thank you.
You're welcome. So in this case, if it's going to decrease by 16%, right, and it's going to start at 100, you would have 100 times 1 minus 0.16, right? 16% you convert to a decimal, and you raise the exponent would be x. So that's what's happening here. Okay, now sometimes you may not have 1 plus or 1 minus something, because what can happen is you can have an exponential function that looks something like this. Remember how this was originally how the exponential functions were presented? You can have something like this, a times b to the x. But looking at b, though, you can determine if the function, but you can still rewrite it, though, as 1 plus r or 1 minus r. I mean, it depends really on b and the given information. Because, for instance, if your b were positive and less than 1, well, this function has to be decreasing, and your b is going to look like 1 minus r for some r. And if b were greater than 1, okay, meaning, excuse me, if the function were increasing, your b then would be greater than 1. It would have to look like this for some r. Okay, so let me show you. For instance, let's suppose this was our function, right? Our exponential function. Okay, well, notice here the b, what you're raising to the x, the base, this is 0.85. Well, that's less than 1. Okay, it's an exponential function, but we're going to rewrite b, this base 0.85, as 1 minus r. We're going to rewrite it as 1 minus r, but we got to figure out what that r is. And that's what this calculation does. So this calculation allows us to figure out what r is. So basically what I'm doing is I'm just algebraically solving for what that r is. So we have 0.85 plus r, right? So here we have 0.85 is 1 minus r, right? So we're adding R to both sides, and then we're subtracting 0.85 from each side, and we get R is 0.15. So really then what this function is 100 times 1 minus 0.15 to the x. So R is 0.15. So here, let me go back to here. So R in this case would be 0.15, okay? And that would tell us the function values are decreasing by 15%. Whereas over here, we have 1.3. Okay, so in this case, it's greater than 1. Okay, so we know that we can rewrite it as 1 plus R, but we can figure out what R is. By being able to write it as 1 plus R or 1 minus R, it just makes it easier to analyze. You know, because remember, once you know what R is, you essentially know by what percent the function's values are increasing or decreasing. So here, 1.3 is 1 plus R, right? It's going to be plus because this base is bigger than 1. Yes?
So in general, if the number that is next to the 100 in that position is
Not
bigger
next to
than
the 100, raised to the x.
next to the x, pardon.
No, raised to the x.
Oh, raised to the x.
Yeah.
So if it's greater than 1, let's say like 20, then it will be a positive growth. If it's less than 1, it will
Yeah.
be negative. Is that
Exactly.
like a rule?
It is.
Oh, okay. Thank you.
I mean, I don't think it'll be 20 because 20 is like really big, but
No, it was just an example.
that's the right idea though.
Okay.
Yeah. All right, so we have 1.3. Okay, so to figure out what R is, right, we can subtract 1 from each side and get 0.3 equals R. But that tells us that this is going to increase by 30%. But again, because again, the whole point of this is if we want to know by what percent the function values are increasing or decreasing, we have to figure out what this R is. And that's what we're doing here. That's what we're doing here.